was saying this is the last Friday. I hope I have to teach extra. But it's very possible we may need one more, okay? But late in why do I hear an echo? Can you hear okay? All right, I hear somehow an echo. So, all right, so we're going to try to continue with sampling methods. And again, pursuing these topics a little bit unusual for a machine learning course, but in the context of computational statistics, it is extremely important. So we have at least 3 more lectures. Normally, with Monte Carlo methods, you expect a whole course as a minimum, okay? So if nothing else, I hope I entice you to read more on this topic. So we will do important sampling today. So we keep building on methods that we declare they're not very good, all right? So you may say, well, you don't start with the real thing. Well, we don't start with the real thing because nobody will follow anything, okay? So we need to start with, it's like saying functions, polynomials are not good. Why you don't tell me about, something else? So, so next week, we will most probably talk about Gibbs sampler, which is part of your homework as well. That is due on Wednesday, and then we will maybe spend about 2 lectures on sequential Monte Carlo, which is sort of the last and most essential part of sampling methods. And later on, if we have time, we'll come up to some other more modern methods for sampling. So today we have to talk about important sampling. All right. So let me remind you the fundamentals that we have done up to now. And really this slide summarizes everything about Monte Carlo methods. And I know you think the notation is not important, but when you come and you give a presentation in December for your project, if I don't see you actually just being at home with this notation, I'm not going to be happy. So in other words, if you bombard me with words and et cetera, I want to see sort of these little notations because they do mean, I mean, actually, there's lots of fine detail in the notation. Sometimes I don't emphasize it a lot, okay? I notice even this there versus that needs some discussion, but hopefully from the context of what we do, you can understand. All right, so we discussed about the Monte Carlo approximation for the distribution pi of x that looks like that. So the samples come from the distribution pi, and we substitute the approximation is these delta functions, and the weights are 1 over n. Okay? So today actually you will see a similar approximation where the weights are not going to be 1 over n. So the idea was to compute the expectation under this distribution pi of x, and the expectation basically comes from the standard Monte Carlo result to be this, and we saw that it is this is an unbiased estimator of the expectation. So if you take the expectation with respect to the underlying distribution from where the data come of the estimator, it comes to be equal to the exact expectation. The variance is the variance of phi of x divided by n. Okay? So I want you to remember, there is an echo, right? All right, let's try this one. I need to be less agitated. Maybe that will help. Just calm. All right, not move. All right. So and actually if I'm not, speaking loudly, maybe nothing is going to come on the video, and then we're going to have another problem. So the expectation is the exact, and the variance is the variance over n. All right. So then we extended, we started talking about how we sample, and in particular we emphasized on the last lecture this rejection sampling, where new concepts came to play a role that we are going to explore further today. So we don't really, so we have a target density, but we actually sample from what is called a proposal density. Okay? And in addition to this target density, we need to compute a bounding constant. So basically C times Q has to be on the top of the distribution pi of x for all x. All right. So the concepts here that they were important is that the introduction of this proposal density, and more importantly, the fact that these samples that we get from Q of x, they are not all accepted. So today we're going to try to improve in the sense that we sample from some proposal distribution, but somehow we accept all the samples. Okay, so we will see how that may work. So the algorithm basically for the accept-reject method, I may refer to it also later in the lecture today. It's very simple. We take a sample from the proposal distribution, a sample from the Green distribution, and basically you accept or not that sample with this probability pi star of y divided by this constant m times q star. Pi star and q star are the distributions pi and q without the normalization factor. Actually, it's important, and you will see this even today, it's important to develop sampling methods where you don't know the distributions with a normalizing factor, because the normalizing factor requires the calculation of a big integral, and then, you know, that beats our purpose here, because here we are in discussion of computing integrals with these methods. So having those integrals coming in the actual distributions would be messy. Okay. So the issues we discuss is that we're wasting a lot of the samples, okay? And we actually computed how many iterations basically in the algorithm we have to wait for a sample to be accepted, which I remind you, because it was a geometric distribution, it was 1 over the probability of acceptance. And of course, you know, we demonstrated that this method doesn't work in high dimensions, right? So we need to do better, at least in some aspects. And one aspect that we're going to do better is that we're not going to waste our rejected samples. So hopefully we will address this. I don't promise that we will address the high dimensionality problem today. So the methodology you will see has similar difficulties as what we saw on Wednesday. All right. Important sampling. So we're going to sample from pi. We're going to introduce a proposal distribution Q, and anywhere pi of x is positive, Q of x has to be positive. Okay? Otherwise, we don't anticipate, right, to, I mean, you're going to get in difficulties actually in the algorithm if this condition is not satisfied. So here's the calculation of the expectation of very simple one line, the expectation of f under the distribution pi. This is our objective. This is what we want on the left-hand side of this equation. This is what we need to compute. So what I do is, inside the integral, I multiply and divide by q. So suddenly, by looking at this new function that I call f subscript q, I make this the expectation of f subscript q under the distribution q. You see that? So suddenly, from having something that is an integral with, it's an expectation with pi, now it's an expectation with q, where q is my proposal distribution. Okay? So you can write this in various forms, but the definition here that I'm using, that we're going to see it thousands of times today, I call the ratio pi over q at the location x. I call that the weight, the importance weight w of x. Okay? So you can immediately see that this expectation becomes the expectation with respect to q of w times f. Okay? Where w now are these weights of defined as pi over q. now we have an expectation of fq with respect under the distribution q, so we will do simple Monte Carlo. And this is what exactly you see here. So the expectation of the function fq, all right, under this Monte Carlo approximation of q, which we call it q hat subscript n, is given by what you see in this equation. So I want you to look at it and tell me if anything looks new or strange. You remember our original expectation became the expectation under q of f of q, where f of q is w times f. All right? So I start with a basic Monte Carlo definition, 1 over n times the summation of fq's of samples from the distribution q, and then I expand f subscript q as pi over q times f, and just I call it again, just, this is my weight w at xi times f of xi. Now you see that this looks like a Monte Carlo approximation, but the weights are not 1 over n, they're 1 over n times w of xi. Okay? Now, we will see this at least even with the equations, but also with some of the results. If the variance of these coefficients w is huge, obviously this approximation is not going to be very useful. All right? So, but right now, simple Monte Carlo calculation. So two departures from Monte Carlo. The standard calculation of the expectation. X's come from a proposal distribution, and then the weights here involve W, which is the ratio of pi over Q. We haven't said anything what the Q is, so in principle here, versus accept reject, Q can be anything. Anything except the fact that it has to be positive where pi is positive. So there is no such a thing that it needs to cover, pi of x and things like that. It can be, in principle, anything. There is no constraint that I see these equations that tell us otherwise. Now, yes, it can be anything, but you will see from the results, wrong choice gives basically garbage results as well. Okay? So we have to be careful on that. So this was the Monte Carlo approximation of Q that we have seen in earlier lectures. Can somebody tell me what is now the Monte Carlo approximation of pi of x? Not of Q, of pi of x, which is our original distribution. What's the Monte Carlo particle approximation of pi of x? What it is here. I remind you how so this, remember, it's an approximation of the expectation with respect to pi of f of x, all right, and it comes to be this. So what do I need to put in my original expectation for pi as an approximation to get this result here? Say it a little bit louder. The weights. So it will be again delta functions, but these delta functions will come with weights, and this is how the approximation of pi is going to look like. So interestingly, this is the approximation, the Monte Carlo approximation of the original distribution pi that we started. These are the weights, but the samples come from the proposal distribution. They don't come from pi. Clear? Again, the notation is not just notation for nothing. There is a reason we have this notation, right? So the samples come from the proposal distribution, okay? This is the approximation of the original distribution, these delta functions, but all of them have weight corresponding to each particle W of xi. All right? Now, is the estimator unbiased or biased? What do you think? Remember basically what we did to get this estimator, we applied the standard Monte Carlo result. So do you expect it to be biased? I know we're going to have problems with this tape, and interestingly enough, I received an email today saying that all technical problems with 126 have been resolved. The implication was that the cameras now work, but let's see. So, is there any reason why this would be biased, this estimator? Okay, so the estimator is unbiased. Come on. Okay, I think the first equation, there it is, okay? So if you, this is our estimator, right? If you take the expectation with respect to the underlying distribution, basically you get the exact expectation of f, okay? I mean, you expect this because it was just the regular Monte Carlo estimate, so that is unbiased. However, the variance, let's see what the variance is going to be. All right? So, the variance would be the classical variance from Monte Carlo simulations, and because we write this as the expectation of W times F, you remember we transform this to a problem where we do Monte Carlo estimate of the expectation of W times F under Q. So the variance of the estimator is going to be the variance of WF under Q divided by L, the standard Monte Carlo result. So I'm expanding it this and I'm writing like that. Is this a correct result? Convince yourselves, because from Q I went to pi there. Remember, W is pi over Q. Is that okay? Do you agree with both terms? I mean, here you will get, right, the expectation under Q of W squared F squared. And W squared is pi squared over Q squared under Q, so you're going to get pi squared over Q times Q, because an expectation, Q will cancel, I'm sorry, pi squared over Q squared, all right? So one of the Q's will cancel with the expectation that you take, and then you're going to have pi over Q times pi, which is W times F squared under pi. You see that? Just simple algebra. When you take W squared F squared expectation of that under Q, this is equal to this term. And then of course you're going to have minus the expectation of this under Q, which is equal to actually the expectation under pi of F, the whole thing squared. Yes? No? It's algebra. It will help if you have a piece of paper and you check it up, okay? You say, yep, nope. Looks good on a Friday afternoon? Yes? Yeah, all right. Okay, here's the problem. Obviously, we need estimators that have finite variance, and this is not a problem, right? Because, I mean, the expectation, obviously, you know, if we have problems to compute the expectation, forget the variance. So the problem is this term, and I'm writing this term analytically, and I want you to remember, and of course I rewrote this again here. This is pi over Q under pi, so pi squared, and then I put another Q there, so it's W squared. Well, I went back to actually the original form, right, under Q. So this, you know, this integral has to be finite, okay? And, you know, certainly, if the expectation of the weights under pi, or if you want it to be even stricter, the maximum of W is not finite, basically this variance will go to infinity, okay? So we're interested basically here for the expectation of the weights to be finite for this integral to make sense. Of course, everything depends on where the function f is, and I'm going to show you some examples with discontinuous functions where you can get in trouble. But if the function f is smooth, basically, you need to be sure that the variance of the weights, okay? And again, pay attention how this is written, right? W is pi over Q. You have an expectation, so you get pi squared divided by Q. This has to be finite. Okay? It's not obvious that this will be the case for all choices of distributions, as we will see with some numerical examples. So before, when I started, I said there's zero constraint on Q, right? This is what I stated. Well, that's true, but now here's a constraint that says, yes, Q can be anything. Just be sure that that this is basically is bounded, okay? Or, you know, if you want to be stricter, basically that the maximum of the weights is bounded. Okay. Before I give you an example, let me just show you how you're going to compute the normalizing factor. So for example, if this is the posterior and you need to normalize it, you have to compute this integral. So you put Q and Q in the twice there, and this becomes the expectation of under Q of pi over Q, all right? So basically here there's nothing to do but standard Monte Carlo. So if you take the average weights, basically that gives you the normalization factor. That's a very important result to remember. Not only in the context of important sampling, but later when we do sequential Monte Carlo, you will see that basically you can reuse the weights to compute the normalization factor Z. So very easy way to compute the normalization factor Z. All right, so let's do an example. So what I want to do is I want to compute the integral of this function f that is basically a mixture of two Gaussians. And what color is this, the lower? I don't know. Green, all right? So green, this guy is green, so that's the function. And a mixture of two Gaussians, we need to basically find the right Q to integrate this. And obviously, we extrapolate from the ideas of the accept-reject methods, right? So we need to be sure that the coverage of this Q distribution is the same or broader than the coverage of the function f. So we select as a proposal distribution something that looks like that. And this is, I will assume, a blue color, right? This is this mixture of the two Gaussians in blue form basically the proposal distribution Q. So again, we want to compute the integral of this function f. All right, so what you see here is we take 1,000 samples in the Monte Carlo calculation. We repeat this several times. The exact integral is this red line, 0.127 or something like that. That's the exact integral. And there is some variability, of course, with important sampling, but what I want you to see is that when we do this with standard Monte Carlo, actually the results are all over the place with 1,000 samples. I hear some noise, so what is the question? Huh? I can repeat the question. If there is a question, you know, there was an echo in my ear saying it's Friday, we have to leave this room. Okay, so you can see again the huge variability with standard Monte Carlo, but when you do important sampling, basically you get better. And if you go, think, the next slide, and you take averages with 2,000 samples, you know, things are drastically, I mean, not drastically, 1,000 is good enough, but, you know, the error that you get, the error bars is smaller because the variance of the estimator is smaller. All right, and I don't have to tell you this because we already discussed how to calculate, how to sample from a Gaussian mixture. So let's see another example. We want to take samples from this double exponential distribution. What's a double exponential? This doesn't look to me like an exponential distribution. The exponential distribution never goes from 0 to infinity. We did this the other day. Yeah, so it's two pieces, basically, two exponentials that you patch them together, one positive, one negative, and that's called double exponential. Okay? So we're going to try to do calculations, basically the compute, let's see, I don't know what the is, I suppose the integral, the expectation or something, and we're going to cover this uses proposal distribution Gaussian, okay? And then use a student t distribution as well. The difference, of course, between Gaussian and student t has fatter tails, so basically we're better suited to cover this double exponential distribution than the Gaussian. But let's see how the results are going to look like. All right, so this is actually, so here the idea is to try to, to get samples and approximate. Basically, what we want here, we don't want to find any expectation. We want to find the Monte Carlo approximation of the double exponential distribution. All right? So what you see here is if you sample from a Gaussian, all right, this is and if you use 1/n times the weights times, the delta functions at the q's, at the point x's that you get by sampling the Gaussian distribution, you get a distribution that looks like that. Does this look to be like an exponential distribution, double exponential? Does it look to be like this? All right. So unless, of course, the student who wrote this program did something wrong, this doesn't seem to work. Right? So Gaussian will not do the job. And obviously the case has to do with, I suppose both, in the center, but also the tails of the Gaussian distribution may create this problem. So let's say the Cauchy distribution that has fatter tails, this looks better, way better, okay? So you can see again, yes, the importance distribution is arbitrary, but you can see a difference that makes day and night effectively in these calculations. All right. You may ask the following question. Obviously, so we computed the variance of the estimator, right? Let's say an expectation or something like that. Can we actually minimize the variance with respect to Q and see if there is an optimal Q? What do you think? Is that worth pursuing? Right? Before we wrote an expression that had Q in it and it was the variance. So can we find that Q that minimizes the variance of the estimator? The answer is absolutely yes, you can. We can find the best Q. All right? How do we do that? Actually, I can tell you first what the answer is going to be. This is the optimal Q that minimizes the variance of the estimator. Obviously, we were taking integrals of f, right? So the optimal Q is absolute value of f times pi divided by the integral in the whole support of pi of x of the absolute value of f times pi, the normalization factor. So the Q optimal is the absolute value of f times pi normalized. Now, is this an easy distribution to work with? Well, I mean, the major problem immediately is the normalization factor there that you're going to have to compute, okay? And in a secondary way, the absolute value is a problem, but maybe you can deal with it. But this, the fact that you need to compute this normalization factor is an issue, okay? So let's see, how do we prove this? I like proofs, because proofs are, they really educate you on how to find the next best algorithm, right? If you cannot do these proofs, you cannot be thinking on what is next in your research. So how are we going to find this? In this slide, we'll need to do a lot of calculations. What would be our starting point for this calculation? What should be the equation that we have here? We said we computed this Q optimum by doing what? Minimizing what? The variance of the estimator, all right? So let me start with the variance of the estimator, all right? Would you agree with me this was the variance of the estimator that we had before? Right? And you can check, it was basically, since we transformed the whole thing as expectations under Q, basically the variance of the estimator is 1 over n times the variance under Q of W times F. And if I expand this, I get that. So how do we go, Nick, from this to that? Because you're looking at me like, I come from another planet today. Must be a long day, I suppose. Nobody knows on the video who's Nick, right? They think it's me. And they may think I'm talking to myself, which I do. All right? So what do we do here? What is the trick to go from here to there? You can take, functional derivatives, right? So in essence, what you can do is you can perturb Q to Q plus epsilon times delta Q and set the first order term to 0 and do like that. I haven't done this, but I have something simpler. Well, it's a cheating actually. It's not really a proof what I'm going to do. Can you tell me, is this whole thing positive or negative, this variance? It has to be positive, all right? So if it has to be positive, let me call this function here g squared, all right? So if I take the variance of the function g of x, we agree that this inequality is true, right? Okay? So effectively, I'm going to plug in g to be pi over q times f, all right? Okay? So this is always greater or equal than this thing squared, all right? And since I do this inequality, my g is really pi over q, because they are positive, times the absolute value of f. You see that? Make sense? Right? I mean, this is the general results, right? So I plug in for g, pi over q times the absolute value of f. So I have this, which is this part of the equation, greater or equal to, I take expectations here with this, it doesn't matter actually if it is, this is g. How do I go from g to pi times absolute value of f? Well, it's here actually, right? I'm sorry. You can go, okay, so I have square q times g, where g is pi over q absolute value of f, q and q cancel, so this is pi times the absolute value of f, right? Just, algebra. So, obviously, this is greater or equal, and the optimal q comes when you have equality, and you can immediately verify, if you plug in this inside q, you will see actually for this choice is the only choice that gives you the left-hand side equal to the right-hand side. So you don't really need to compute derivatives with respect to functions and things like that. So the Q optimal is given by this nice equation, and again, this is a fantastic theoretical result, but it's really not very useful. Okay. All right, so we need to keep improving now this important sampling technique. And suppose we don't know the pi and q, for sure, let's say we don't know pi as a normalized distribution. So basically we know up to normalization factor pi, and let's assume for now the same is true with q, all right, even though we choose q, so it would make sense for q to be an easy distribution that is normalized, but let's say pi is not normalized. Will this method work? What do you think? If pi is not a normalized, we don't know the normalization factor. Can we make this to work? Do we need the normalization factor pi? If you remember, the rates are pi over q. Right? What do we need to do? Can we make this to work if we don't know pi? We know pi star, which is the normalized version of pi. Can we make this to work? actually, we don't see this often in machine learning books, because they always, in the text they have toy examples, but in reality, again, if pi is your posterior, you're not going to have a normalization factor. So let's see what happens. So this is my actual distribution pi, and I write this as the normalized part of it divided by the normalization factor. On the numerator, divide multiplied by q star. All right, and as I mentioned, q is really not a problem. We can normalize it, but q star is the normalized part of q. And I do the same multiply, divide on the denominator side of the integral. So this becomes now w star, which is now the weight of the anormalized distributions, pi and q. All right? The weight of the anormalized distributions, pi and q, times q star, and then I have w star, q star dx. And actually from this, I can write it like that. Can I go easily from here to there? Remember, q star is the numerator and the denominator. So if you divide both sides with the normalization factor of q, obviously you're going to get q there and q there. All right? So this is a nice equation, because now it tells us that if we know the unnormalized weights, pi star over q star, we have an expression for pi. Nice. How's that possible? How is that possible that somehow, from not knowing how to normalize pi, we have an expression now that involves weights that are unnormalized, right? But it's possible because just a little trick here, and it gives me this nice equation. But let's see, can we actually do estimations using these w star weights and not w? So let's see that. All right, so let's see the calculation. This is what we want. This is our objective. We want the expectation of f under pi. Nice. What have I done here? This divided by this integral, which was that? Remember? You forgot? All right, that's pi. So I substitute pi equal this divided by that, all right? So what do I have in the numerator? It's the expectation on the q of w star f, and what I have on the denominator is the expectation with respect to q of w star, and obviously because there's w star on the top and the bottom, this is obviously also equivalent to the expectation on the q of wf divided by the expectation of w. Okay, but let's concentrate in that equation. To find this estimator, we can do it by only using w star. But now, instead of a simple expectation where we can apply Monte Carlo, the problem becomes what? What can you tell me about this problem? This is our now estimator. This estimator is now what? How are you going to compute that estimator? I see expectation and an expectation, so what do you do? So if the distributions are not normalized, if pi is not normalized, the estimator becomes what? How do you recall when you have this divided by that? The ratio of two estimators. So before we had one estimator, right, that applied Monte Carlo, now we have the ratio of two estimators, the estimator of w star f and the estimator of w star. Right? So if we use our Monte Carlo approximation for q, okay, this is exactly as before, and we plug in the numerator, we plug in the denominator. This is what the answer looks like. Our estimator is going to be summation of some weights times these delta functions, but these weights By the way, you notice here there's capital W. All right, some new notation. The capital W is W star at xi divided by the summation of all the W stars. So basically these are what weights? Normalized weights. That's the only difference basically. So you don't really need to know the normalization factor of pi. Very useful. All right? You don't need to know the normalization factor of pi. You can still apply this Monte Carlo estimator, but it's really the ratio of two Monte Carlo estimators, one in the numerator and one in the denominator, but when you put them together, effectively you get these normalized weights. Very simple. Okay? Now, I am not going to prove the things that I want to do next, but let's go back to what was that equation with the two estimators? Was here? Yeah. So look at this estimator now. It's the ratio of two estimators. Do you anticipate any difference whatsoever from what we did with our regular estimator before? Is there anything you have to worry? Like, you know, before we said the estimator, the Monte Carlo estimator was unbiased, the variance was the variance of f over n. What can you tell me now? Are we going to be able to say this is an unbiased estimator, this is the variance? You know, what do you think? Is it trivial now? Because now we have the ratio of two estimators. How do we apply the central limit theorem, etc., to say something about the variance or something about the bias of this estimator? Is it unbiased? What do you think? It's not obvious what I'm asking, right? But I want you to see where the difficulty is. Do you see anything different now from before? Before we had one estimator, Monte Carlo, we knew what the answer is. Now we have what? The ratio of two estimators. So can we say the same things for the ratio? The answer is no. Okay? So I want you to look at the proof because, you know, it took me, I had a number of typo mistakes. So I have to rederive things and maybe I have to recheck them once more. But here's how the calculation goes. So we're looking at applying Monte Carlo to the ratio of two estimators, okay? So we're going to use what is called the delta method, that if you have a good statistics book, it describes it in a very general setting. And basically, the delta method basically tells you if you have a function of two random variables, and you know the mean and the variance of each of those random variables, how do you calculate the mean and the variance of this function g of a and b? In our case, we have two random variables, in essence, which are our two estimators. So our function g is what in our case? Or what do you think it's going to be? It's going to be a over b. Okay? So this delta method basically works with a Taylor series expansion around the means of a and b. At least you can compute the variance using that. Okay? So from here you can, if you take the expectation of that is two terms growth, the expectation of z is, again, with the first order expansion is the g computed at the mean values, and the variance is basically given by this nice expression. Okay? Simple algebra, basically, you should be able to even visually agree that these expressions are correct. Okay? So what we need to do is, to start with, apply these two results, okay, to a function g that is the ratio of a over b. So this is what we're going to do. Our estimator, our function z, it was the ratio of two Monte Carlo estimators, one that involves expectations of W star F and another one expectation of W star. So I call the numerator A, the denominator B, and we know that each of these terms is unbiased, right? So we know the mean is the exact mean. We know the variance is what? The Monte Carlo variance, which is for each estimator sigma square over n, all right? Effectively, for these functions, for A over B, you can differentiate. And I said we know the means and the variances, and here are the means and the variances. You can plug them in and do the algebra and compute the variance, and this is the result that you get. So let me just finish it. It comes out when you use a first-order Taylor expansion, okay? When you use a first-order Taylor expansion, it comes that you get a central limit type result. So this, for the so we are looking. So basically, our estimator looks to be unbiased, right? But I'm going to come back to this and correct it. But the variance, this is what I hope I did not mess up the notation there. But the variance of the estimator, all right, the variance that you get from this, when you plug in everything in here, looks like this. All right? So it is pi square over q of square of f minus the expectation of f squared. Okay? Which, if you write this as pi times pi over q, is, no, actually this is correct, okay? So this is the variance under q of w times f minus this. You should write this is equal to what? I can write this as pi square over q square times q, right? So this is the first term of this variance. The second term is equal to 0. You see that? The second term is 0 because the expectation of f and that gives you 0. Right? So the first term, basically when I expand the variance, the first term will be this. Right? And the second term, which will be the expectation of this times the expectation of that, the expectation of the second term will be 0 because you have E of f minus the exact E of f and it gives you 0. So basically, the asymptotic variance of the estimator now is not your classical exact variance divided by n, but you can see it's 1 over n times this important sampling variance that is given by this nice formula. Okay? So remember when you do calculations and you use important sampling, you don't use the Monte Carlo standard variance. This is the exact variance. Okay? Now it comes out that the bias from this, actually this is, I think it's correct the notation here. The bias of this is equal to 0. All right, this is like the central limit. When I look at this estimator minus the exact, which is the mean basically of that, the bias is 0. But there is a problem, and the problem is, you know what it is? The expansion that we use is a first-order expansion. So when you do a first-order expansion, you're happy. You say there's no bias. But if you take anything, especially a ratio of two functions, and you do Taylor series expansion, are you happy with the first-order expansion? So it comes out that actually if you push the envelope and you're not tired of doing heavy calculations, all right? So if you actually, you do a second, you keep second-order terms, all right? And so now you can immediately see, yes, when you take expectations, this will cancel, but then you get this term will give you variance terms, and this term will remain there, and it comes out, there is asymptotically biased, and the bias is basically given by this term that you see here. Okay? And as a matter of fact, you can see that the bias here is 1 over n squared times that. So the variance is 1 over n times that important sampling variance, and the bias square is 1 over L squared times that. Right? Bias squared, you always compare it with the variance, so the bias square would be 1 over L squared times this calculation. Again, the algebra, it is trivial. Again, you just do the Taylor series expansion, you plug in the mean and the variance for the term for A and B, right? The two Monte Carlo approximations that we're doing, and when you plug in there and you delete lots of terms that cancel out, this is what you get, all right? So asymptotic, obviously this is unbiased, so if n is very high, this converges to the exact estimator, but if you use a finite n, basically there is a bias. Okay, so don't be surprised there. This doesn't have the nice properties of standard Monte Carlo. So you lose basically things when you do important sampling. You have to pay something, and in this case, the variance is not your standard variance, and then you have a bias term as well. Okay. Now, since we discussed the optimal proposal distribution for important sampling, you may ask me now, and what is the optimal Q when you use this normalized important sampling? Well, this is the answer. Okay? So the difference from before, and by the way, you can start maybe thinking why this is the case. You notice everywhere we had to subtract, it comes out minus the exact expectation of f under pi. All right? So this looks exactly as before, but now in this two terms is the absolute value of f minus the exact expectation of f under pi. Okay? And the proof is basically identical to that given before, so you basically have to start with the asymptotic variance, but we derive with the delta method, and try to see which Q minimizes this or makes the left-hand side equal to the right-hand side, and that Q comes to be that nice expression that you see up there. All right. Now, I'm going to give you, without proof, the following result that you will see listed in a lot of Monte Carlo books, especially in applications in physics, in biology, in chemistry. So they give, of course, they don't list the exact asymptotic variance of this estimator when you use this, normalized version, basically of the estimators, this ratio that we discussed. So the approximation that is given for functions that don't vary very much is this equation here that maybe some of you have seen in textbooks, even undergraduate textbooks. And basically it says, well, you know what? The variance of this estimator is not your Monte Carlo variance, which is the variance of this divided by n, but it's really this times one factor that is 1 plus the variance of the weights on the Q. So effectively what it means is if you collect n samples of this, n weighted samples basically, they come up to be equivalent to n divided by this factor of unweighted samples with standard Monte Carlo. So in essence, to get similar results in the variance context that you get with standard Monte Carlo, you have to use more samples when you use this weighted methodology. Okay, and this again, it's even in undergraduate books, they will you will see this formula, and they will tell you basically how many samples you need to reach asymptotically the same variance as Monte Carlo estimations. So the idea is given by this simple formula, okay? But it's an approximation, and again, you don't need it because we derive the exact formula, sort of we derive the exact formula for our problem. Okay, so let's see if I need to tell you anything else. So we discuss when we did Monte Carlo, we discussed the normalization factor. You can easily compute it with, in terms of the particles, basically. So how about here now? If we utilize pi star and you know, can we find the ratio of the two normalizing constants? Can you compute the ratio of this directly as post-processing, basically, of your calculations? So once you get this particle approximation with these weighted samples, can you get this? And the answer is yes. And look at this trivial calculation that I'm doing here. So we need the ratio of these two. So I multiply with Q star, all right? And this integral, basically, all right, is my original integral, okay? So this Q star, I put it inside the numerator integral. So basically, this is the numerator, and this is the denominator. You see that? Maybe I should not have put bold on this, right? So this thing here is the numerator, this is the denominator, okay? The only thing is just Q star cancels. So pi star over Q star is W star. Q star divided by this is Q. And effectively, the ratio of the two normalizing constants is the expectation of the weights. So basically, 1 over n times the summation of all the weights computed of your particles, that gives you the ratio of the two normalizing factors. Again, if you don't know sort of these trivial calculations, right, and you do particle approximations with Monte Carlo, you may spend lots of time to approximate these normalization factors, for example, for model comparison and things like that, but you don't need it because immediately you have a very nice Monte Carlo estimates of these normalization factors and the ratio of the normalization factors. Can you do important sampling for Bayesian inference, right? Because at the end of the day, this was our starting motivating reason for discussing about Monte Carlo methods, right? So this is the posterior, the likelihood times the prior. It looks to me this fits perfectly because we never wanted to calculate, unless we talk about model evaluation and comparison, we don't want to calculate that integral, okay? So what should I use as Q if I want to sample from the unnormalized posterior? Assuming, you know, that will make sense in our problem. So what would be an obvious distribution to sample? What should I use as Q? If I want to sample from pi star, which is f times pi, the prior, what should I use as Q? Assuming again that that will make sense. But what would be an obvious starting point? No, you remember optimal doesn't work because you need to calculate the normalization factor. So it's optimal for the books. In practice doesn't work. But if I want to sample from this posterior and I know only the unnormalized posterior, we already have done actually this one. We discussed about the accept-reject even methods and Monte Carlo methods. What would be a nice Q to sample from? The prior. Assuming it's not completely informative, right? So we're going to take Q to be the Q star would be Q equal to Q star equal to pi, assuming this is, you know, normalized. And then the weights become the likelihood, okay? And that makes calculations extremely easy. So in lots of books you will see calculations and approximations given for the posterior in terms of particles, and you wonder how do they get this? Well, they get this because they take as Q the proposal distribution with the prior, then the weights come to be the likelihood, and then everything else falls from there. Okay? And if you want them to go back and compute the normalization factor, no big deal, because in terms of the particles, you can compute anything you want to. Now, this assumes, of course, that the prior, will not mess you up. Lots of the priors are not only uninformative, but you cannot normalize them also. Right? They're improper. So can you do this with improper priors? That's something you will need to check very carefully. Okay. So do you think important sampling can work in high dimensions? So accept, reject, doesn't. So what do you think? Is important sampling going to do the job in high dimensions? Well, we sample like Q, and then we form, our Monte Carlo estimates, normalize or unnormalized weights. What do you think? Obviously, for every problem, right? If you find a counter problem where that doesn't happen, and especially a trivial counter problem, then we have an issue. So here is exactly the same problem that we used in the accept-reject methods. So we want to take samples from a Gaussian, and actually you can see this Gaussian is so simple, is the product of the univariate Gaussians. Right? So very simple. Okay? Variance 1. And obviously, I'm going to use exactly as I said, the same thing we use for accept reject. For using sigma greater than 1, I'm also going to use a proposal that is a Gaussian, and obviously has the same support as my pi, and for sigma greater than 1, it's on the top of the pi, so it has all the nice properties. So if this doesn't work, nothing is going to work. All right? Because this is like an obvious. There's no reason why it will not work. All right, so what do we need to do to know if it works? What calculation are you going to do in your problems, in your projects, to figure out if, you are sampling correctly? What do, we said, we have to calculate the W's, and the variance basically have to be finite of the estimator, and at the end of the day, the variance of the weights has to be finite. Because if the weights basically start blowing up, if you have an estimator that's in terms of the W's, right, it says summation check W's times the delta functions that you have. If the variance of each W goes to infinity, what estimator is that? Not very useful, right? So what do we need to compute here to see if this will work? So we calculate the weights, all right? So the weights pi over q equal to this, which you can show is less or equal to sigma to the power d. And then what we have to do is we have to calculate the variance of the weights, all right? So here is the calculation of pi over q under the proposal distribution Q. You plug in, and again, double check that this calculation is correct, because I was trying to check, I believe, with this book on Monte Carlo methods for scientific computing, and somehow it was giving another formula. But I trust if I changed the formula there, most probably I was not happy with what the book was giving, but who knows how I was feeling that day. So maybe my result is wrong, all right? But the conclusion I know is going to be right, but this may, you guys tell me if this, when you check it out, okay? So if you calculate this variance, you know exactly that it is this to the power b over 2 minus 1, and this thing inside the brackets there, inside the parentheses, it is greater than 1. So you have something greater than 1 to power b, where b goes to infinity. So the variance of the weights goes to infinity, so forget about it. Okay? So basically, important sampling doesn't work in high dimensions. And you may say, wait a second, this doesn't work, that doesn't work. What does it work? Well, high dimensions is a complicated problem. I wish I can say that everything is easy, right? So we will find some methods that work, but you have to appreciate the fact they work, but maybe not, depends what you mean high, all right? and it depends what the problem is, okay? But there is an issue with high dimensionality and these trivial sort of proposal distributions that are Gaussian already demonstrate to you that we have a problem. Actually, in the slides that follow, and I'm not going to prove it because we're running out of time, but actually I give you a proof that you can make the important sampling algorithm to be basically identical to the accept-reject algorithm. Okay? I don't know if I'm not gonna give you everything, all right? So let me see if I can. Well, I'm not gonna go through the details, okay? You may want to read it because it's very educational, okay? By augmenting, basically by, if you want to sample from x, you enlarge the space to x and y, where y takes value 0 and 1 with, I'm sorry, y takes values from this interval 0 to 1, not 0 or 1, all right? And this will remind you the accept-reject probability, but in any event, you can show that the important sampling algorithm, you can actually put it on an identical form as accept-reject in a higher dimensional space, but the variance basically of the accept-reject is worse than the variance of important sampling because the space is also high dimensional, so this is not sort of a recommended sort of type of approach. Okay, I wanted to do, and I hope I will finish today with this. There are many examples in the notes with little MATLAB codes that you may want to play, but I want to do the following problem. No, we don't want this, come on. All right, here's the problem I want to finish this Friday. We want to solve A x equal B with important sampling. I think I mentioned that practically every problem in linear algebra and in integral equations, etc., can be solved with sampling methods, and actually way more efficiently than many of the methodologies you know from linear algebra. In particularly, for example, if you look at Ax equal B, right, and this is X is a million dimensional vector, and you say I'm only interested for X 1000, the component 1000, not everything. Do you know any method that actually will only compute one of the X's, not the rest? But there are, I can think of lots of problems where you only are interested in some components, not all of the components. Okay? So how do we do this with Monte Carlo? Here's the trick. I'm going to multiply this with a matrix G, and actually somewhere in the slides I even tell you exactly what the matrix, how you choose it, so that, so the right-hand side, it would be another vector 8, so G is given, okay? But I multiply with the G so that GA can be written as the I minus a matrix B, that the matrix B has a spectral radius less than 1. Basically, that means that all its eigenvalues are less than 1. And the reason you will see in 1 second why this is going to be helpful basically in setting the Monte Carlo pattern, okay? But I can find the G, and I think the example that I give you reference, for sure if A is symmetric, you can do this automatically, but you find the G so that GA is I minus B, where B has a spectral radius less than 1. So basically I want to take advantage of this form I minus B, and so this is going to look I minus B times X equal to H, and the solution of that in a series form is B to the power K times H. Does that look familiar? You remember if you expand series expansion 1 divided by 1 minus X, what do you get? You remember when you were in high school, you were happy with all those great things? 1 divided by 1 minus X, what's the series expansion? This? Yes? Now, do you see why I need the spectral radius of B to be less than 1? Right? Because we need these powers, because if you think the B represented with eigenvalues to the diagonal, if you rotate, right, you're going to have the eigenvalues to the power k. You want to be sure they don't diverge because the series goes to infinity. So if this thing is more than 1, this thing will converge. Okay? So, we want to compute x then as an infinite sum of b to some power k times h, and a b again is a given matrix because I'm designing G, so I know what b is, right? So I want to solve this, and I want to solve not with a series expansion, because that will complicate the problem. I want to do this with Monte Carlo methods. So let me write this as follows. You will love it because, with Monte Carlo methods, you can do fantastic things if you allow your imagination to operate. Okay? So I'm going to write this xi equal the sum, and then this b to the power k times h, I'm going to write as b times b times b times b, k times, with all the summations involved until I reach k times hk. Can I do that? Yes? Yes? All right. Tell me now, let me see if I give you another hint. All right? That's not a hint. All right? Wait a second. So, I'm going to define gamma k to be a vector of these indices I1, I2, Ik. All right? Okay? So, I just want to give you, I hope I hide the equation that I need. Okay? All right? So, okay, this is good. All right? Don't look in your notes. So, I am going to, so basically, I am going to call, okay. Here I have the product for a selection of indices I1, I2, Ik, but I have all of these summations there for the indices I1 to 1 to n, 1 to n, etc. Okay? So I call gamma k to be this, and I claim here that xi is the summation of this alpha I, all right, where alpha I is defined by what you see here, for all possible indices gamma k. Make sense? And then I got rid of the summations explicitly. I said, take all the possible permutations of the gamma k's, sum them up, right? This will give you the correct xi, where alpha I correspond to gamma k. If k is positive, is this product. If k is 0, it's basically just hi. There's none, I don't have any b's. If k is 0, I get hi. Make sense? I want you to look at this equation. It's 4:43, it's Friday, we don't have a lot of time, and think about a way to rewrite this equation in one step that immediately will bring Monte Carlo methods in a way that will allow us to compute this. So here, I sum over all possible indices gamma k defined by here, this equation in the middle. So when you see sum over all possible values, right, of a discrete variable, where's your brain going? This is what type of a quantity in statistics. When you average over all indices, it's expectation. But I don't see any distribution. Well, sorry, you should see 1. And that distribution 1 is the uniform distribution over what space? Of all possible indices. You see that? So here is your problem. This is, xi is nothing else but the expectation of alpha I, all right, under the uniform distribution of this indices gamma k. All right? And basically, you know what? Important sampling. What is Q? All right? Q is an importance now. You remember, so the exact distribution is under the uniform distribution of indices. I'm going to introduce my proposal distribution, something else. So I need the weights times Q, all right, So the important sampling becomes the expectation of the relations alpha I over Q under this discrete distribution of indices Q. Right? And Q is a distribution, proposal distribution over indices, and I am going to give you, because people, the tape will expire in about 1 second. This uniform distribution basically is going to be a random walk in k steps, right? Because this is what we're looking here, where I'm going to go from I to I1 to I1 to I2 with some transition probabilities, and then obviously I have to stop at k. So I'm going to have a stopping probability, which is 1 minus these transition probabilities, and I can put any values to those that I want to. Right? So we're running a little bit ahead of our time, right, by saying random walk, but you can appreciate, I can say, I can go from I to I1 with some probability, I1 to I2 with another probability, etc. But I need to be sure that I stop at index k, and the probability of stopping would be 1 minus the summation of the probability.